a naive mathematical model of the Mold effect in its stationary state. The chain fountain phenomenon, also known as Mold effect, can be observed when a chain pours out of a jar. Self-siphoning is observed. The chain rises above the jar and then drops to the floor. I put a link in the description of this video to a video showing the Mold effect. Here we assume that a steady state has been achieved. The chain retains its shape and the velocity of every link of the chain is the same in magnitude. For this velocity we write v. The top of the fountain is at a height h1 above the jar and at a height h2 above the floor. So the chain rises to a height h1 above the jar and then the drop height is h2. Mu is the mass per unit length of the chain. A segment of length ds of the chain has a mass dm. Then we can write dm equals mu times ds. In the jar, a segment of mass dm of the chain is accelerated from being at rest to a velocity v in a time period dt. To maintain this continuous change of momentum, a force F1 is needed. We can write F1 times dt equals dm times v. For dm we can write nu times ds and we obtain F1 times dt equals nu v times ds. Then dividing both sides by dt gives F1 equals nu times v times ds divided by dt, where ds divided by dt is the velocity v. So F1 equals nu times v squared. At the top of the fountain we have again a change of momentum. Here at 1 the velocity changed from 0 to v, and here at 2 the velocity changes from plus v to minus v. This continuous change of momentum requires a force pointing downwards. Because the change of momentum in 2 is twice as big as in 1, we can write F2 equals minus 2 times F1. So we have F1 equals nu times v squared, and F2 in magnitude is twice as large. F2 equals 2 nu times v squared. The vertical segments of length h1 and h2 of the chain have weights fg1 and fg2 respectively. We can write fg1 equals nu times g times h1 and fg2 equals nu times g times h2, where g is the acceleration due to gravity. We compute the velocity v of the links of the chain using the principle of energy conservation. For the links of the chain, potential energy corresponding to a height of h2 minus h1 is converted to kinetic energy. This gives v squared equals 2g times, in brackets, h2 minus h1. We have the following equilibrium of forces. F2 equals Fg1 plus Fg2 plus F1, where F2 equals twice F1. Subtracting F1 from both sides and writing nu v squared for F1 and nu g times in brackets h1 plus h2 for the sum of the weights Fg1 and Fg2, we obtain this equation. Then we substitute for v squared from what was obtained from energy conservation, and we obtain the following equation. We divide both sides by the product nu times g. And rearranging terms gives the following result. So this height h2 is 3 times as large as h1, according to this model. Researchers who thoroughly investigated this problem concluded that a vertical upward force from the bottom of the jar plays a crucial role in this process. The present model does not consider such a force. This force could easily be detected just by monitoring the weight of the jar during the process.